My name is Alex. I'm here with Ed, who's in the back and will join us in the middle of the talk. We're both from Google Brain, the SIR team. This is joint work with Tim Nebraska, who's a professor at MIT, Jeff Dean, and Alkis Polyzotes, who are both also at Google. And this work really is about database systems in particular, but I think this has interesting implications for any system that sort of is running on data, doing operations over data. And really for all of these, there are these sort of fundamental building blocks that we've all learned about and sort of rely upon in any of these systems. Everything from sorting and joins as sort of key operations to data structures like Btrees and Bloom filters that are sort of well studied for decades. Now, one thing I found interesting as a more ML data mining person coming into sort of the world of infrastructure is the degree to which infrastructure is really built as this is one size fits all. We should have one piece of infrastructure that really should work for a huge number of applications. And this actually is interestingly in contrast, I think, to the ways in which much of machine learning focuses a lot of attention on individual applications. And so,
isn't that an artifact of the so-called expert systems of the 80s?
is it an artifact of?
Yeah.
Which side, the database side or the ML side?
The ML side.
I was not around in the 80s to say
Just checking.
how it works.
Okay.
I came in '89, so I might have missed most of the waves.
There's this guy upstairs. Find it, Bob. You
He's not upstairs anymore.
So Btrees obviously have been well studied. To give some background, although I'm guessing most people in the room already know this, you say you have this huge array of data, right? There's a bunch of keys and some payload over that data that we're trying to do lookups on. And we build this tree with some branching factor that will help us efficiently go from the root node to find that data, and then you can do a range query. Data sorted, so you find the starting point in the range, and you walk through this array. Now this is a good idea, it's general purpose, it has nice properties in terms of cache efficiency, tons of useful things. What happens if your data though is all integers from 0 to 1 million? You can see this here on the slide, it's 0 to 480, right? So in this case, you really don't need the tree structure. I mean, the tree will work just fine, but it's kind of besides the point, right? You can just do a direct lookup with the key. If it was from 100 to 1,100,000 as the range, you could do the lookup key minus 100, right? So for pretty simple patterns, we can see obviously that the Btrees overkill. You can do it in O of 1 lookup time, O of 1 memory in those cases, these corner cases. So this one size fits all thing, while it works, it's also overkill, right? It's not necessarily the best fit. On the flip side, we don't want to go and check every time we build a data set, does it meet one of these sort of properties we expect and therefore we can use as other database. And the cool thing is machine learning lets us think about this over distributions more generally, kind of abstract away that concept of consecutive integers and say, even for these other patterns that may not be quite as simple, we can still aim to do that same thing, the kind of simplified lookup pattern. And so this is the key insight, is to switch from thinking about this as sort of the data as a black box that we're operating over, and we think about scaling in terms of just how many items are in that data set, to thinking about the data distribution, right? How noisy is this data distribution, or how complicated is the data distribution, and not just the size of it. And this can actually significantly change the ways in which we design these algorithms. So I really think, honestly, this has implications for tons of things. I think since we started working on it, we increasingly find new places where this can affect the way we think about the design. But we're going to go through a couple cases in really Btrees in a ton of detail, Hashmaps and Bloom filters in some detail, and we can sort of opine on where it has effects for things like sorting and joins. But start with Btrees as an example, right? So as I mentioned, this is this tree structure, and the real reason this is a huge benefit over things like binary search in practice is because it matches well the actual systems that these databases are run on, right? There's a cache hierarchy, and Btrees are well suited for that. We can tune things like the branching factor to match page sizes, etc. But sorry for that looping thing. But we see a Btree really is just this input-output property, right? Takes as an input the key, and it outputs really a page, right? In practice, these are usually stored on disk. So we say, here's this page, it lies on this page, and then usually we do some search within the page to find exactly where in that page the key, the record lies. So abstracting further, we can say this is a general mapping, right? Key to position, and then then we know that the record with that key lies in the range from position to position plus page size. If we abstract one more step, we see this can be pretty loose. We just need some function to magically go from key to position. And at least as long as that position is pretty close, and we kind of know how close it is, we can say at the worst it's overshooting by this much, and at the worst it's undershooting by this much, then we can search in that range and find the exact right record. And one cool thing that came out of once you frame it this way is that you find that what the Btree is really doing is building a model of the cumulative distribution function, right? So if your data, say, sampled from a Gaussian is here, you find that most of your data will come in this more narrow range in the middle, and as a result, it will sort of allocate more parts of the tree there to understand that. But the cool thing is people in ML and statistics have been studying CDFs for a long time. We can leverage a lot of that understanding. It has interesting properties, like it has to be monotonic and other constraints on the modeling. But the point is this is a pretty general purpose model that really is just at the core describing what's the distribution of your data. Where is it coming from? How does it look? And so we had this idea, and we thought, okay, this seems like a cool new thing. What do we do with this, right? And there's all these reasons we were excited. They should be much smaller. Models are tiny by comparison to Btrees, right? Maybe it'll be faster because we can do floating point operations instead of if statements. We can do parallelism. We can do batches of operations at a time. Obviously, GPUs and TPUs are on the rise, right? So we had all these hopes for what this would do, right? So we were really excited about the work at the start. And then we said, okay, let's just do the ML thing. We'll just throw TensorFlow at the problem and say it'll just figure it out, right? This is the ML magic. So we had 200 million records. We'll say, okay, we'll take a 2-layer neural network and just sort of typical fully connected thing, train it to predict the position given the key. These are integers. It's pretty normal. Btree runs on the order of 300 nanoseconds. This first version ran in 80,000 nanoseconds, right? So this was kind of a bit of a step back. So 2 steps forward, 1 step back kind of situation, right? We thought, okay, we had this huge breakthrough in insight. We'll just do it. And then it doesn't work. And the more we spent time with this, we found there's tons of pieces to this problem that I think are actually fascinating directions on the system side as well as on the ML side. For one thing, TensorFlow really is not. Oh, what's up?
Sorry, just for the experiment there, those numbers, that was with 1,000,000 integers, or what was that with?
So it's trained to the data set size is 200 million keys, but we're measuring here the time to run the index. So in the Btree case, it's just walking through the tree. And the model, really, this is just instantiating TensorFlow, effectively, right? It's independent of the size of the data.
Right, I'm just curious if the data set size will affect the lookup time with the Btree.
Right, yeah, the Btree definitely does, but it's not even close, yeah. Okay. I don't think there's a size of data that would have made this come close. I mean, there is, obviously, but... yeah, I think the thing is that TensorFlow really is not designed for that size of operations. Right? I mean, I think we're moving in that direction. There becomes increasingly sort of efforts to make it work, for example, on varieties of hardware and to have it handle different performance requirements. But generally, like looking at can we analyze searches and recommendation systems, which is the other area of other areas of research that I work on. There, you see that it's just different orders of magnitude, right? So.
Did you analyze that 80,000 nanosecond? Where is it actually going?
That was really mostly just instantiating TensorFlow, right? So I'll come into like what actually is happening. I don't think it's like that is by far and away not the best that we could do. I think with out-of-the-box tools now, even from a year ago when we ran that. But it was definitely not like the most thorough study of that. I think it was just like if you do the standard thing, it won't work. Obviously, there's tons of work on TPUs that are trying to make that faster. Those are generally throughput focused. Different constraints for different systems. So there's just pure speed. There's actually model structure, right? Btrees are actually really good at overfitting, it turns out, and that's usually like a bad word in ML. You don't want to overfit. It turns out for databases, that's actually not so bad in many cases. right? If you're a read-only database, I know the data. I know exactly what I'm trying there's nothing else outside to generalize over. Cache efficiency. I don't think I've ever heard of a paper for ML thinking about a cache-efficient designed model. There's a lot of work now going into matching the hardware for things like GPUs, but this is sort of a new problem. And then search, right? I mentioned at the end there's this process of actually have to search over normally in the page, but here it could be much larger possibly, or much more narrow, right? It can vary depending on how accurate the model is. And so there's questions of like, what's the best search style given an approximate answer? So I'll kind of go through a few of these things we've tried to tackle. So for one thing is speed, right? Here, essentially, we wanted to go from using raw TensorFlow to just sort of compiled operations, right? So we can use TensorFlow to learn a model, extract the weights, and then have that sort of better organized in memory in terms of the weights. You'll see in a few slides how there's different pieces to the model to organize, as well as actually have those operations being run in like raw eigen, which is what's underneath a lot of the TensorFlow, but in simpler operations. There's obviously things like AVX and stuff we didn't actually, or SIMD we actually didn't even make use of. A lot of this builds on work Tim had done previously on compiling ahead of time database operations. And so I think there's a lot of potential here generally for ML to sort of catch up for doing these really, really low latency kind of things. The next question became like, what is accurate enough? When is it even worthwhile to use a model in the first place? And we'd spent a long time debating, does it matter to have the bottom of the tree be accurate or the top of the tree be accurate, or where do we think it actually is beneficial? And here's some like rough math that if you have 100 million records and your typical, let's say, page size or branch factor is 64, then that gets you from essentially knowing it's in this 100 million records to it's in this give or take 1.5 million records, right? And so pretty much if you can get a model that can be more accurate than being the right 1.5 million range, that's probably worthwhile. And you can see that at every level, right? And there's of course this challenge, right? It takes 60 cycles for that thing to actually do this search within that page, within that branch, and know which branch to take. So we have to have fewer than 60 cycles of modeling time used to actually figure out that 1.5 million record range. We can do this obviously at each level. And the question becomes like, okay, how big model do we make? Right, so what's the right model? Should I do a super wide model? So okay, people know that these are supposedly universal function approximators. Just make it super wide and it should be able to model anything. This will then cost, in terms of math operations, 2 times the width of this. Or we can say, okay, well, deep is actually better for complicated patterns. So in this case, it's width squared in terms of the width of the layer. And you can say for every intermediate layer, you have to do like that square matrix, right? So that's an additional matrix math we have to do. Now, the problem with this is what we found is that doing a single model is good, but not great. What we really want to be able to do is make use of the memory, right? One of these models is tiny compared to a Btree, right? That's like, the gap is huge. But what we want to do is be able to move in between those two things a bit more elegantly, right? We should be able to say, I want to ramp up the model size, and with that, not totally kill my speed, and at the same time improve my accuracy greatly. And this became this design space challenge we had to figure out. And so we use this idea called hierarchy of experts. There's a bunch of literature on modeling multiple experts in ML. This is a structure we used in particular where we say, I can have a very small model, even a linear model, to try to say, given a key, predict the position. And I train it sort of in the typical way, predict the position. And then given that approximate position, use that to select another model. And that model will then be trained on the subset of data that was thought to be in that range, right? So what you're slowly doing is you're whittling down, similar to a Btree, the range of data that each model is expected to model well. And we can do this over and over again, recursively, until we sort of get these models that are sort of approximating less and less data. And what these really do, if you have linear models, for example, is you're getting this piecewise linear function, but we don't have to do this sort of search over which piece we're in. It's selecting it through this sequence of multiplications. And the good part of this is it decouples entirely the model size and its complexity in terms of what it can model effectively.
Are you training each one of those models individually, or are you training that whole thing as one model?
We train it stage-wise. So with the top layer first, that can be like a linear model, one pass. So yeah, in practice you can say each one's linear. Each stage is one pass over the data. So you do one pass, you find out on the next one which bucket it would fall into, and train that on one pass. If it's nonlinear, it's obviously a little more complicated, but still you do stage-wise. We've tried some things with actually training it end-to-end. There are some interesting challenges. So the related work here is the mixture of experts work, where they'll train a softmax over different models. But that's inefficient. If you have large numbers, we'll see we go up to 100,000 submodels in some cases. So once you have a softmax, you have to actually now search what's the max in that softmax. That's slow. Where here we're doing essentially a regression prediction, right? We're saying this is the index of the model I want to look up. And for that, you have to now add some variance in order to do some searching over it, and it gets complicated. So I think there's potential there, but at this point, this was like good enough. Right.
I understand. I have this question. When you're coming down in the hierarchy, does it mean that the training set becomes smaller and smaller for each of the submodels?
Yep. Each model becomes now it's handling a much more narrow region of data.
Wouldn't that be a problem because your training set becomes a problem? Like,
It's a problem if you're worried about overfitting. We're not worried about overfitting because only the data in the database do we have to index. This is like one of these cool things that we want to overfit, and this is why the model looks quite different from what everyone does in traditional neural networks.
Is it guaranteed that the prediction of the top level model will, like the range that it predicts will include the actual key you're looking for?
It's not predicting a range, it's predicting a number. And so
Okay.
it could be pretty far off. So we can do, because again, it's a fixed size data set, we can look at essentially how far off were we. So one pass, train the model, second pass, look at how wrong were we possibly in that pass, or in that trained model. And we can use that now to narrow it down.
Training until you can narrow the range for each one.
Yeah, actually, the next slide, right? You see, in some cases we can say, oh look, I didn't actually do it well enough, right? I see there's a big error, and I can substitute out saying, for whatever reason, there's some pattern here that just I can't get right. Fall back, it's all fine. And I think a lot of the work we'll come to is there's this hybrid pattern, right, where ML can provide a very good approximation for a large number of the cases, but maybe not every case. And using this in combination with traditional data structures makes it sort of give the guarantees you want while getting a lot of benefit.
And so if you were to like write the read-only thing and add something to this, would you just retrain the model that's specifically affected by this? Or?
So we have a bunch of slides later, but it's an open question, right? So we only tested, at least empirically so far, the question of if it was read-only. If it's not read-only, you could leave space and say, okay, the model's getting less accurate. It'll just degrade gracefully, which would be not the end of the world. Your error estimates go away. We can deal with that in a few slides. You can imagine doing training again. Again, that's going to kill your error estimates, and depending on how you do that training, it could affect how well it's doing. So I think there's a huge design space there of what's possible. I'll go into more detail, but I think there's a bunch of like interesting questions. So one more question. All right. So the question is, so we have a pretty good prediction, but we now need to do this sort of last mile issue. I have to actually go from an approximate answer to getting you the right data you actually asked for. So I can say there's some pretty wide error bars here, and I can do the typical binary search thing. I know the min error and the max error, and then I can slowly walk through from the predicted position until I find the right point. Now the problem with this, of course, is that we were actually really close, and now we wasted a lot of time trying to do this full range search. And so a lot of this has to do with then trade-offs, depending on how accurate your model is and what your error distribution looks like, to matching your search algorithm with that. So we can do coordinary search. This is something Tim played with a bit, where we look at the standard deviation and we add multiple predictions around it, and we can move all these simultaneously efficiently. This is not the most clear illustration of how that works, but essentially you can slowly hone in. And the last thing is, if we don't know the errors, I think this is actually a useful case because in many cases things like inserts might destroy our error estimates. In this case, we can still do sort of exponential search, right? So I have this prediction, and I just slowly move step by step away until I overshoot and go back, right? So I overshoot here, and now I can slowly walk back to the right place. So it's pretty flexible in terms of like there's multiple search strategies with different properties. We'll see a couple experiment results that do show that they have some trade-offs depending on the model, but overall it wasn't like a make or break part of what made it succeed. So we tested on 4 different data sets with real patterns. So one's a timestamp data set from some server logs, longitude from maps. This one's like the most linear, so he gets the best results. This is a synthetic data from a log normal distribution. Right, so in this case, we know it's nonlinear. And then string documents. Strings have their own issues because they're kind of arbitrary in many ways. And they're document IDs, so it gives some structure to them at least.
So I had this discussion once with Joe Hellerstein up at Berkeley, and that question is basically a lot of progress was made simply because of improvements in device physics. And the database people made a distinction between in-core databases where everything was in memory versus off-core, on secondary storage devices. And it's only recently that we had solid-state disks to replace rotating media, as an example. So are you going to get into databases with addresses larger than 32 bits?
So it's a good question. There's 2 points to that, I would say. One is the question of how did the model deal with large address spaces? And the second becomes how do we deal with actually not being able to assume that the end location is ordered, right? So if you have pages that are on disk, those might not actually be in order. They could be on separate devices, something like that, right? In terms of the disk-based part, we have some preliminary ideas that we can't sort of give empirical numbers for yet.
That's the key word I wanted to hear there.
But there's, in terms of there's also the issue of like most models aren't dealing with like really large numbers. You obviously have to scale then like your operations to be able to handle that. But I think even that also is not quite as bad. It's manageable. It's an engineering issue.
We can talk more there.
Sure. Yeah, so these are definitely not, these are all in-memory tests we ran. So the course of the question is obviously, does it work? This is on the maps data, I believe. Yep, the maps data. And we see the Btree, this was the best Btree size, the page size 128 for the particular device we were testing on. We ran this with linear models in this case. So each model in this tree is a linear model, but we see the second stage size has a huge effect on essentially the performance, right? So there's one key root node of a linear, and then followed by many, many small models in the second layer.
That's size measured in weight, so what is that size measured in?
It's how many
nodes?
models there are. Each model is linear, so there's a bias and a slope.
How many models there are? Okay.
So it'd be the bolded one is 50,001.
And how big are each of your models in terms of parameters?
It's a linear model, so it's a single floating point number and a bias term. So 2 floating point
So
numbers.
just 2 parameters for your linear model.
Yeah. There's some other results that go through like nonlinear models that pays off, especially in the string case, other things. But I think it turns out the hierarchy is actually very powerful compared to like what if you were doing just a bigger neural network for the individual one. So having a larger tree seems to be the right choice. And we do see here there's this trade-off. Essentially, you make the number of models in the second layer larger. Obviously, makes the actual thing itself larger. We generally see that it decreases the time. So you have this trade-off between memory and latency. In some ways, I think this is nice. I think this generally what we get with the model approach, the learning index approach, is you actually have some nice ability to move more cleanly in the space of let me use more memory, decrease latency, and also trade off actual compute. And I can actually move in that space much more flexibly depending on how I design my model structure itself, what I'm willing to deal with. And so we do find in some of these cases, right, we can get to be 1/100th the size or multiple times as fast, which I think is a nice thing, given this is like all from that earlier 80,000 nanoseconds compared to 300 nanoseconds. We didn't look closely at training times. For linear models, it's pretty fast because it's a single pass. So this would be, I think, like 4 passes at most, including the error computation. And that can be all done in the LIF system that actually does the training. All the linear stuff was done sort of in process, whereas a nonlinear model, you use TensorFlow and offload it. Generally, this wasn't a huge concern, and a lot of systems that like we work with have a separate sort of model construction time when it's a read-only system.
So is this like the average lookup time, or like
This is
how
the
it is-
average.
Okay. Are there statistics about how it performs in the worst case?
We did look at it. I can't remember the details honestly. There was we did look at like different percentile marks, but I don't remember the details unfortunately. We also didn't really look at in any way. This is another assumption I think it's worth mentioning. This assumes the sort of uniform query distribution, right? So we're not also optimizing for some preference for one part of the data over the other. It's only looking, so it's the same amount of information that a B-tree has. Overall, we get sort of these levels of improvements across different data sets. The maps data I think does the best because it's the most linear, and so it's the easiest to model. And you do see, I think there's this interesting property, right, that depending on how complicated the data is, or data are, that affects how well we can do on it under the current model class we're looking at. Strings are, I think, present the biggest challenge. They can be a sort of arbitrary word length, and the computation needed to deal with it is not great. And there's a bunch of other details about how you actually model strings, right? People model them typically for language purposes, not for the sort of index lookup in ML. And so this is an example of that, where we actually start to find that using things like the coronary search has a decent impact actually. And some of these hybrid indexes start to matter, right? So we do find that in these harder cases, these extra steps do end up paying off. Whereas in the earlier maps case, sort of out of the box modeling works pretty well. I mean, obviously with the compilation and everything else. There's also been a bunch of discussion afterwards about like what's the right baseline and how would you actually sort of take this insight and use it in other places, right? So someone suggested, for example, using a fixed size B-tree, and then you can do interpolation search afterwards, right? And so these different combinations of these ideas. So we tested this on this log normal data, synthetic data. The payload size affects how well it does. It affects cache efficiency. But ultimately, we end up seeing that we can still always find sort of better balancing of both memory and latency. This partially also makes use of using a multivariate model, right? So we can look at things like the square of the key. That helps give some more flexibility beyond just a linear model, but without increasing the model itself more like in a significant way in terms of complexity. I think that again, by no means is this the end all be all of models. I think there's just a big open area to make better models for this kind of system. Yeah, and that's just a visualization of that. And last thing, I think this is by no means sort of a deep theoretical analysis, but I think it's nice to think about under this ML perspective, what would theory look like, right? And so here I looked at saying if we have this empirical CDF, it's kind of flipped from the way you normally think about CDF style analysis and statistics. Say I have the empirical CDF, that is the ground truth, right? I need to model that as well as possible. But if you imagine that the model of it is the theoretical CDF that it was sampled from, you can say, well, that theoretical CDF isn't getting more complicated. But what we do say is that it has some accuracy. There's some noise inherent in the sampling process, but it's a reasonably good, accurate model. It's not overfitting, unfortunately. But what we can find essentially as the data size grows, that affects the accuracy. And this happens to be the way that accuracy sort of works out. That this expected squared error between the empirical CDF and theoretical CDF scales with 1 over n. But if we're now multiplying this by n, where right, we have to look up in an n-size data set, that means the error in that lookup, it scales with O of square root of n. So I don't think this is particularly the best way or even the most charitable way of analyzing what we're doing. But I think it does provide a path forward to think about, okay, how do we think about the distribution and the difficulty of it and how that affects the scalability of our algorithm. And there's tons of open questions. Inserts is obviously one of the ones that people always bring up. I think there's potential, right? So appends is a whole class of problems. You have timestamps that are being inserted, so sort of sequential data that's coming in. Chances are there's pretty consistent patterns, right? You can imagine there's sort of cyclical daily patterns. If we can generalize, and ML studies a ton about how you generalize into the future, it's possible we actually can do this without having to build out your index over time. And there's lots, yep.
Sorry, I didn't quite understand the claim here that inserts get much cheaper. Why do inserts get cheaper?
So the idea here would be to say if I have one model that can generalize into the future, which is what ML mostly tries to do, we don't actually need to keep constructing the model, right? I don't have to keep building the B tree as I insert data. And so I'm literally just going to be adding data, inserting it at the end of the next page on disk. So I still have to do the writing to disk. I still have to, or adding it to the end of the array. But the model should hopefully still be able to predict as n grows, just predict into the future. It could still be at noon is peak time and at 6 a.m. is quiet time, and that's the cyclical pattern I have to predict into the future. And it'll have some error, and I can do search to correct that at the end.
I see. I guess I misunderstood. I was assuming that underlying the model was predicting a position in a sorted array, but that's not true. You're not using a sorted array underneath.
This would be a sorted array, right? If you're indexing on timestamp.
Yeah. Okay. So inserts still need to use a B-tree to figure out where to insert that so that you maintain the order of the array.
What I'm saying is
just
if
append it to the end of the list, right? Because then it wouldn't be ordered anymore.
I think the key thing I'm saying here is if it's a case where you want to be ordered by timestamp, which is a set of problems. So like, give me all. So the index thing is coming in order. Then I don't need to. So that's why I say append only, right? Not arbitrary inserts here.
But if you were doing arbitrary inserts wouldn't necessarily get you.
So arbitrary inserts, you could say I can leave space in my sorted array. Btrees can do this too. You can leave space, obviously, and then hope that that space is well allocated. And that if the space is well allocated, such the pages don't fill up, I can just sort of keep things in order in the page, and the B-tree above it can stay the same. But when I spill over pages, I have to now do some reshuffling of the internals of the tree. And the hope here becomes, well, maybe I can do something smarter in this way, again, in the modeling side. It can be approximate. ML has a lot of work, again, on generalizing the future, looking at covariate shifts and saying, not just what's the distribution now, but where I think it's going to grow in the future. And I'll leave space there. And so I think, again, this is not by any means that we've done this, but I think there's the language of ML or the sort of types of work that's been done in the past could be adapted in useful ways to try to deal with this issue. And so now I'll turn over to Ed, moving on from Btrees to some other structures.
A little bit of handoff here to keep you guys awake, more or less. In the beginning, we started showing this picture, right, to give you a sense of all the various possible data structures that we might be interested in affecting using this learn index idea. And Alex just spent all this time basically taking you through this particular use case of Btrees. But what about other kinds of data structures? For example, hash maps. Now, it's actually kind of interesting. We're telling this story a little bit in reverse chronological order because we started with obviously something a little simpler. And we told you actually the most complicated case. And hash map was actually the second one we looked at. And we'll talk about Bloom filters later. But if you think about a hash map, keys basically are mapped to a position inside an array, right? So that's the prediction task that essentially that we care about. Now, if it turns out that spot is taken in that array, what we do is we do a linked list overflow, right? So collisions, unfortunately, in hash maps are actually really expensive because you're basically doing pointer chasing. And every pointer that you chase is actually about 100 nanoseconds using the current architectures. So we want to avoid that collision as much as possible. That's essentially the job of what a hash map is trying to do, right? So if we think about hash maps essentially as a learned model, now the same ideas that we were talking about in the B-tree case actually applies as well. So basically, a machine learning model in this case is kind of learning essentially the CDF, the cumulative distribution function, right? And we can directly actually use that learned function as our hash, right? So in that case, if you have perfect information about your data, which in a way we do because we know every single key that we care about in the hash map, then a perfect CDF model would give us 0 collisions, right? And this goes back to the question that I think you were asking about a little bit before, is that if we assume that we're only doing reading, then at that moment in time, we have the perfect information, and therefore there's no collision. But of course, with inserts, you end up with more and more collisions, right? Now, what's interesting about this is that this fact that if you have the perfect CDF at that moment in time, you can construct the perfect lookup table, essentially, right, is independent of any kind of modification that you want to do to the hash map, right? Whatever kind of hash map type you might want to use. So the question is whether this is really true. So like good researchers, when we started thinking about hash maps, we wanted to build essentially the quickest benchmark that we can to rapidly reduce whether we have a difficult problem here or not. So we tried this idea out on 3 different data sets. On the map data, I think Alex has talked about a little bit before. The web data, I think we'll actually get into a little bit more detail later in the slides. And then just some arbitrary log normal distribution that we created. So you can see that in the traditional hash map, you get collision rates roughly in the 35% range. Whereas with a learned model, you can dramatically reduce the number of collisions in the lookups. So that reduction looked pretty dramatic to us. It was like, oh, that's good news. We should chase after this idea. Maybe this idea wasn't so terrible after all. So that was very encouraging early on when we were starting to look at hash maps. When we look deeper into this, so the data that I'm showing here is basically you build a hash map, and you either use a random hash function, or you use the learned model hash that we learned through the procedure that we described. And you can see that the amount of empty slots that we end up having to use has a pretty dramatic reduction in the amount of space that we need for those empty slots. And yes?
How much space is the model itself costing?
Oh, that's a good question. The model themselves are actually very cheap, right? Because you basically just need to know the CDF, right? Like the CDF is what you're learning. Yeah, exactly. So it's super cheap as a result, right? The interesting thing here is that you can see that at least in our implementation, compared to a random hash, the model actually you have a little bit of computation to do, and that costs you a couple of nanoseconds. And so it's actually not true in this particular case where we can beat the random hash as a function. Yes.
Just a high-level question: if you're kind of assuming that the distribution of your data is pretty much fixed, and you know the keys, why learn it? Why not just compute it?
In a sense, sort of a tablet, just tabulate it completely, right? Yeah, that's interesting because in a way it connects to your question about inserts earlier. In the particular case of hash maps, we are thinking about the transaction where you're inserting these items, right? So if it's truly completely a static world where you know all the keys ahead of time, you're right in the sense that you just tabulate the CDF and just use that function, right? The size is kind of an issue. A learned model might actually compress. You have for example, if you have a linear function, right? That's literally 2 parameters, as Alex was saying before. That's much smaller than storing the entire CDF, right?
I guess not.
Right. So you may have heard about a little bit of the controversy around this paper, and there were a little bit of conversation online about whether we're comparing against the state-of-the-art hash map implementations and whatnots. And so one of the interesting thing about this space is that you could use various different kinds of assumptions about what kind of instruction set that you're using, what kind of hashing technique you're using, etc. So we ran the experiments after some of the code were made available to us, looking at, for example, the AVS instruction sets, how much payload you're actually using, and things like that. In our experiments, we see that particularly in the in-place chain hash maps, with the assumption of using a 20 byte as the payload that you're looking up, the learn hash function actually achieves very, very good performance of about 35 nanoseconds compared to some of the other implementations. So we do think that some of these ideas seems to hold up under some scrutiny. And the space utilization is obviously also very good because, again, the basic idea here is that since you have perfect information on that CDF, why wouldn't you be able to do better, right? So let me touch upon a little bit on Bloom filters. Yes?
Sorry, in the previous slide,
yeah.
Is there a reason we're only showing the 20-byte records for the learned hash function as opposed to also the 4-byte values?
As opposed to?
So I see 3 rows at the top and 1 row at the bottom.
Oh, right. And you mean instead of running the 4-byte value also as
why are you
as
only comparing against the 20-byte?
I think the reason that we were really thinking about is that we think that the 4-byte case is not really all that realistic in the real world workload, right? I mean, that's a very, very small payload.
Will that change your time utilization?
Yeah, I think I remember.
You see the first two rows, right? Going from 4 to 20. It affects the caching essentially, and so by doing the larger records, it does slow down the traditional implementations.
Yeah. I mean,
it's pretty consistent.
The larger record can only slow you down. It wouldn't make you, right? So a 4-byte, I would imagine, should be less than 35 nanoseconds, right?
Well, if you're hitting the same cache line, then I would assume that you would have the same. If you're hitting the same number of cache lines, I'd assume you have the same performance.
Yeah, so you could be still 35 is what you're saying. Yeah, I mean, that's reasonable assumption. I think thinking about this space, one of the major challenges, as you kind of are pointing out, is whether you're hitting the same cache line or not. Yeah. That's right. So that kind of thing sometimes might even depend on your workload assumptions and things like that. Right? So let me actually tell the story around Bloom filters, because to some extent, this is actually the story that I love the most, because this was the place where we actually started when we started thinking about learning disease. And it's a part that I feel like I also have more of a hand in it. So just as a quick summary of what Bloom filters are, right? So what Bloom filters are basically is that you give it a key and you ask it whether this key exists in your index or not. And so what Bloom filters are nice is that they guarantee that the false negatives is essentially false negative rate is 0. And you can sort of tune your performance of your traditional Bloom filter by choosing a false positive rate that you're willing to tolerate. Basically, when it says yes, how often it is actually wrong about being yes. So how a Bloom filter works in a traditional way is in the following way. So you take a key, and you have multiple hash functions that you apply to that key. And then you have this bit array that basically serves as a lookup, right? So doing insert, when you're inserting a particular key, you hash that key, and you have those bit positions, and you turn those bits to 1, right? And doing a lookup or a probe, what you do is you take that key that you wanted to look up, and you apply those same set of hash functions, and you look in those bit positions. If any one of them is a 0, you will return no, right? If they are all 1s, then you will return yes. So that's how Bloom filters work. But if you think about what it is trying to do from a machine learner perspective, which, by the way, that's what I guess at this point I can call myself a machine learning researcher. I'm wearing a Google AI shirt, so I guess I am a machine learning guy. Actually, just as a side note, the last time I was in this room was Terry Winograd inviting me to give a talk here. And I was back then known as a web analytic and social computing guy. So, you can reinvent your career, right? But if you think about Bloom filters as a model, then all they are is really a binary classification task. That's all, right? You give it a key, and it needs to predict whether it's inside the set or outside of this set. And that's it. big problem with that view is that the false negatives are not guaranteed in a typical binary classification machine learned model. So how do you solve that problem? And this is the part that I'm pretty proud of, because when Tim was interning in my team, he was doing his sabbatical in my team, we were discussing this problem, and I suggested that we could use a spillover Bloom filter. So the idea, of course, is that if it says no, what you can do is you then double check it using a Bloom filter. But the beauty of it is that this Bloom filter can be much, much smaller, because you've taken care of all the other keys that you don't need to know about, essentially. That are the easy cases. So the Bloom filter becomes this guarantee that deals with only the hard cases. I think this design pattern is really interesting, is that it's sort of, unfortunately, I know somebody in the CS department, Chris Manning, who's actually kind of an acquaintance of mine, sort of talked about talked up this paper a little bit, and some people started saying, "Oh, throw away your database or data structure textbooks." But actually, we never said that really in the paper. In fact, part of the paper was saying, make use of the traditional data structure along with a learned index, right? At the same time, they can actually work hand in hand. The beauty of the traditional Bloom filter is that it gives you this guarantee, essentially, of the false negatives being 0, the false negative rate is 0. So this solution of having a spillover is something that I think is a design pattern in these kind of learned index situations that we can make use of in other kinds of, we just talked about all the other data structures that you can conceivably use this idea on. So there may be these patterns in those other data structures as well. So here's some results. Again, every time we think about an idea like this, we want to rapidly reduce to see whether we're wrong, right? Does the idea hold any water? And so in this particular case, we're plotting on the y-axis the memory footprint, the size of the model. In this case, we build basically, the task that we're trying to do is you have URLs that are held in a database, and we want to find out whether those URLs are good or bad. They're bad when they're a phishing URL, so then we want to warn the user, basically. But they're good if they're not in our database, right? And so the y-axis is plotting the memory footprint. The x-axis is the false positive rate. You can see a traditional Bloom filter in red here on the top line. And then the various versions of our model, which are built using RNNs. And the W refers to how wide the RNN model is, how many neurons wide it is. And then the E refers to the embedding size that's used as the vocabulary underneath the RNN. So you can see that different size in terms of the machine learned model, you get slightly different performance, but they're actually pretty close to each other. The 128 is a little bit over capacity, so you can see that its memory footprint goes up a little bit. But 32 or 16 is more than enough for the task that we were looking at. And that resulted in a 36% reduction in memory for this particular Bloom filter. Now, after we put the initial version of this paper on archive, as you can imagine, lots of people started writing emails to us. One of them was Michael Mitchenmacher from Harvard University, who had been spending essentially a majority part of his career on Bloom filters. So as you can imagine, when he was alerted that we were interested in Bloom filters, he was very curious about our results. We ended up having a very, very long email thread back and forth about whether the learn Bloom filters is a good idea or not. And eventually, we're happy to say that he came around to our point of view. And in fact, not only that, he had an additional build on our idea of this spillover Bloom filter. He said, why not also use another simple Bloom filter in front of the learned model and create a sandwich structure? So you run through the initial Bloom filter first, again, handling some really easy cases, and then have the learned model handle kind of the medium hard cases, and the really hard models end up in an additional spillover at the bottom. And he was able to prove recently that there was an additional 12% saving in size in some of the workloads that he was looking at. So I think that paper is now available online, right? So that kind of gives you a sense of 3 cases of the various things that we're looking at. So one thing that we spend a little bit of time discussing already in this forum is inserts and updates. How do we deal with inserts and updates in trees? This is one of those annoying tricks that lecturers and professors like to do, is that that exercise is left to the reader, right? So inserts and updates, I think there's some real opportunities to do some research there. But there are lots of other potential applications. So for example, we haven't talked about at all about joins. How do you do joins well? And in fact, one of the most tricky problems in joins is the problem of estimating the cardinality. If you can do that using a learned approach, you might be able to do much more efficient joins. Sorting is pretty interesting. That's obviously been a lot of work that has gone into beating the best sorting algorithms out there. We think that there might be an opportunity to use a learned approach for sorting. The CDF essentially gives you an approximate sort order. So there may be an opportunity to, again, make use of that information and maybe combine with some traditional sorting algorithms in that sort of maybe sandwich or not sandwiched approach, that combined hybrid approach, to really kind of look at sorting in some new lens using the formula that we've given in this lecture. Another really interesting thing that we have started working on, simply because it's just so fascinating, is that you can think of a lot of the work that we have described here as being wanting to create a mapping function, right? And it's typically 1D or 2D mapped onto some one-dimensional thing that we wanted to know. So yes, no is literally just, are you over a threshold or under a threshold, and that's it, right? But what about multi-dimensional indices, where we have much more complicated 3D, 4D, 5D lookup keys that you're trying to index, and you want to do very efficient lookup in those situations. So you can imagine, since machine learning models, ML models, are just simply creating these mapping functions, that they should apply for multidimensional indices as well. And I think the saving could be even more dramatic in those use cases. The other thing that I think is worth thinking about in closing is that the fundamental ideas from this lecture that I think you might be able to take away from is that if you learn the patterns in your data, you should be able to make use of that in your data structure design, right? That's, to some extent, is not really a huge surprise. And there's been other data structure work that has made advantage of data patterns as well. But one thing that is really interesting here is actually the fact that much of the old data structure design assumes essentially a kind of computing architecture that's based upon CPUs. And in CPUs, the typical operation a lot of times is if-then statements, right? If this, then do this, otherwise do this other thing. And that makes like branching and prediction, et cetera, very, very important in these kinds of architectures. But the thing is that increasingly we're moving to a world where we have vector processors, where vector matrix multiplies are really, really cheap. So to some extent, one of the things that I think is really exciting about the work that we're doing here is the realization that maybe we wouldn't be even running these learning indices on CPUs. We'd be running them on vector processors, where essentially you're replacing the if-then statements with multiplies, vector multiplies to be precise. And so that means that if every server comes with a vector processor. I'm unlike Alex, I am old enough to remember the co-processors next to the 8386s, right? So there was already some point in our past in computing history where we thought that coupling a vector processor along with CPUs could be a real advantage in the design, and we think that's the case in data centers as well. So that's it. I think that was kind of the way to summarize what we're thinking about in the space, and I hope that was interesting to all of you. Thank you very much.